All right, welcome back to another lightning review video. This is a companion video to lecture 7, and today we are going to talk about Turing machines. So our previous automata have had internal states, and they move between internal states based on where they are and based on what they read off the input tape. Our pushdown automata also had a special memory, a stacked memory off the side. But our Turing machines have a couple of new superpowers. So our Turing machines can move left or right on the tape. And they can also write to the tape. And if we put those two powers together, these very simple powers of moving around, rereading input we've seen before, rewriting input, this will essentially allow the Turing machine to turn the input tape into an infinite data storage, a random access memory, with which it can do almost anything, like far the most powerful of the automata we've seen up to this point. So at each step, the Turing machine can do all of the following. It can read in one symbol from the current square of the tape that it's looking at, like the automata we've seen before. It can also change its internal state. So that's doing something inside the box, like moving from Q0 to Q1. And then it can do two new things. It can write on the tape a new symbol in the box that it's looking at, and it can move one square left or one square right. So that's all it takes to give our Turing machines the ability to do everything our modern computers can do. Let's write it out as a 7-tuple. So here's the formal definition of a TM. A Turing machine is a 7-tuple Q, sigma, gamma, delta, Q0, Q accept, and Q reject. And most of these elements should be familiar from previous automata. So as before, Q is a finite set of internal states. Sigma is a finite input alphabet. The reason we distinguish sigma from gamma is so that we can restrict what we have as input on the tape. The reason we have gamma, our tape alphabet, is so that we can read and write things on the tape that are not allowed to be an input, like those $ we use frequently when we're talking about pushdown automata. The tape alphabet will let us use other symbols at our convenience. But in particular, it will always include all of the input symbols and a special blank symbol, which I'll draw as this little square bucket. So the blank symbol is what's on every unwritten square of the tape. If we move way out to the right and see new squares of blanks, that's what we'll treat them as symbols. We can program and react to them just like we would any other symbol on a tape square. We have Q0, our start state, and we have two special accept and reject states. So these are special, accept, reject. Why do we need to pick them out specifically? Why do we have one? Well, it comes down to the Turing machine's special power of moving backwards and forwards. Unlike with other automata, we don't know when we're done reading the input. Every other automaton, we said, we'll consider it as accepting or rejecting once it's read in everything from the input tape. Our Turing machine might change what's on the input tape. It might move backwards and forwards and backwards and forwards. It might move way off to the right, write some more stuff, and move back. So we don't have the end of the input tape as a marker for when we're done computing. Instead, we'll use these special accept and reject states. So when we enter these, we stop immediately. So if our Turing machine enters the accept state, it accepts, all computation halts. Same with the reject state. Finally, as usual, the meatiest part of our definition is delta, our transition function. So delta will map from the state set and the tape alphabet to the state set, the tape alphabet, and something from the set LR. The first thing we might notice is that we don't have a power set on the right-hand side. So as written, this is a purely deterministic Turing machine. Non-deterministic Turing machines do exist. At this point, we're just defining a deterministic Turing machine, which means we go from one configuration to one single other configuration. We can read the transition function as follows. This first part says, give me an internal state. So something in Q and a tape symbol. That is whatever I read from the tape square that I'm looking at right in the moment. And I'll tell you what to do. I'll tell you a new internal state to go to. A tape symbol to write. And whether to move left or right. So our transition function is telling us precisely what we would expect based on where we are. What we know right now, I'm in this internal state and I can see this on the tape below me. I'm going to move to a new internal state, possibly write something new on the tape below me and either move left or move right. And it is possible to draw a Turing machine state diagram. So, I can draw my internal states and I can draw transitions between them. If I write something like 0, arrow, blank symbol, comma, R, I would read this transition as if 0 on the input tape. So if I read in a 0 where I'm looking on the input tape, then I will write a blank and move right. So this corresponds precisely to my transition function. The input is the state I'm in Q0 and the input string, the input symbol Q0. The output is what I write, the blank, where I move right, and the new internal state I'm in Q1. However, it's much more common, instead of drawing out a full state diagram or writing down a 7-tuple, to talk about Turing machines at a higher level. So I'll give you an example of a higher level description. Why do we talk about them at a higher level? Well, for a couple of reasons. Like other automata, it's possible to do low-level descriptions, but the more complicated the thing is that we want to do, the more cumbersome these low-level descriptions get. If I'm going to start programming Turing machines to do very complicated tasks, it's going to take me tons and tons and tons of transitions. But I don't have to stick to that lower level. We're computer scientists, so one thing we're good at is memoizing functions, writing subroutines. If we can show that a Turing machine does something once, well, then we can use that algorithm, that procedure, as a subroutine. We can rapidly build up a high level of Turing machine executions. Once we're confident that Turing machines can do just about anything you would expect them to do in a finitely described procedure, reading and writing on their input tape, we can be confident enough to write out fully specified procedures for Turing machines at a higher level. So I'm going to write down one example of that. In particular, I'm going to write an implementation level description where this term implementation level, it's not perfectly precisely defined, but it's used frequently in CIPSR. What it means is I will describe the tape head movement, that is moving back and forth, reading and writing on the input tape, and the tape contents, so how I read and write. I could at a higher level just describe a generalized algorithm, but at the implementation level, I will still talk about the head movement back and forth and what happens on the tape. And it's probably best to just see an example of this. So here is a Turing decidable language. C is the set of strings A to the I, B to the J, C to the K, such that I times J equals K, and I, J, K greater than or equal to 1. So this is a primitive way of representing correct multiplication problems on the positive integers. If I have 3 A's and 5 B's, I better have 3 times 5 equals 15 C's. And if I want to build a Turing machine that recognizes this language, I could do it with a 7-tuple, but I could also precisely describe what it does when it sees a certain input string as follows. I'll say my Turing machine M3 on a general input string W does exactly the following. First, I will scan the tape and make sure input matches A plus, B plus, C plus. So all strings in my language match this pattern, and this pattern is a regular expression. So I certainly know my Turing machine can do this because a DFA can check if a string matches a regular expression. So it's definitely going to be possible, even without writing, to just go along the tape from left to right and do my normal regular expression recognition procedure to check if my input matches A plus, B plus, C plus. And now that I know that, I can move my tape head back to the left and start counting A's, B's, and C's. So move back to left, and for each A, I will do the following. This is going to look an awful lot like a for loop. Cross off the A, and then shuttle back and forth, meaning move all the way left, move back to the right, move left, move right, between B's and C's, crossing off a C for each B until no B's remain. If I run out of C's, I will reject, and otherwise, I will restore the crossed off B's. What I mean by restore is take the symbol of the crossed off B and write over it with a regular B. So what this will do is it'll count and it'll subtract a C by crossing it off for every B. If I do this loop a bunch of times, I'm going to subtract all of my B's from my C's A times. In other words, I'm going to subtract I times J C's, which is exactly what I would like to do. So 3, if all A's are crossed off, that's when my loop is done, except if no C's remain, reject, otherwise. And I claim this is a complete implementation level description because it tells me precisely how to move my head for any particular input string. This is a shorthand for a formal definition. So while writing this, I'm not going to do it, but I should be confident that I could take this procedure, and if I devoted a lot of care and patience to it, I could take every individual step and turn it back into formal instructions for my Turing machine. Now to wrap up, let's see this machine M3 in action on 3 test strings. So I'm going to test the string AA, BBB, CCC, CCC. That's 2 A's, 3 B's, and 6 C's, so this should be in the language. I'm also going to check a couple of likely strings that should reject. So I'm going to try one with too few C's, and also one with too many C's. So let's follow our procedure. On this first input, 1, I'm going to scan the tape, move left to right, and yes, indeed, the input does match A plus B plus C plus. I'll move back to the left, and for each A, I'll follow my procedure. Cross off the A, move over, and shuttle back and forth between B's and C's, crossing off a C for each B until no B's remain. So cross off that B, move over, cross off that C, move back, move over, move back, move over. Now when I move back, I see all my B's are crossed out. I did not run out of C's, so I reach the end of my loop and I restore the crossed off B's. Now I'm in a for loop. I'm running this for each A, so I'll cross off my second A and once again shuttle back and forth. B, C, B, C, B, C. Move back. I see all my B's are crossed off, so I restore them. And now I have crossed off all of my A's, so I reach step 3. If all the A's are crossed off, except if no C's remain. So no C's remain, and I do indeed accept this string. Now let's consider what happens on my second example string. Here, I cross off an A, then I cross off 3 B's and 3 C's, uncross my B's, cross off my second A, B, C, B, C, B. Whoops, there are no C's left. So in this case, I use my special case. If I run out of C's, reject. And now I can see, well, running out of C's will tell me there's not, like, it will tell me that K is less than I times J. Finally, if I run my third example, I will cross off the A's, cross off 6 C's, reach step 3, and step 3 tells me to accept if no C's remain and reject otherwise. There are remaining C's. My I times J is too small, so I will reject this as well. So I hope now I've convinced you that this Turing machine procedure creates a Turing machine that decides the language C, that accepts whenever a string is in the language and rejects if a string is not in the language. That gets me to my last definition of the video. TM recognizes a language if it accepts all and only strings in the language. And a TM decides a language if it accepts all in the language and rejects otherwise. So this is a decider. Decision is stronger than recognition. So if I have a decider, I'm always guaranteed to say yes on a string in the language, and I'm always guaranteed to say no on a string that's not in a language. So what the heck is the difference here? Why aren't these two the same? Well, it's possible to accept all and only strings in the language, but also to end up in an infinite loop and never reach the reject state on some strings that are not in the language. So if I infinitely loop on strings not in the language, then I might recognize the language without deciding it. So that's all for our Turing Machine Lightning Review video. Thank you for watching, and I will see you in class.